Hello everyone! Welcome to the third video of our Fidelity for Hydraulic Turbines series. Today, I'm going to focus on how to prepare and run a simulation with our coupled pressure-based solver. We will show how to monitor convergence of residuals and different quantities and do some co- and post-processing. Okay, so we are now within simulation context. The first step is to create a new simulation using the Open Solver and add all the different domains. We can see both grids for guidebane runner and draft tube. As we discussed in our previous video, the mesh only consists of one flow passage, but we can show all of them by using the turbo menu, which also gives other visual options. Note that this repetition is only a visual effect. If we actually required a full 360 degrees mesh, we would have to change the number of mesh passages that are generated on the mesh environment, but we won't do that this time. Alright, next thing to do is to switch to coupled pressure-based solver. When creating a simulation with Open Solver, it will default automatically to density-based solver. Click OK to apply all modifications. We may want to add some outputs, for example, relative velocity, Y+, or viscous stress. We need to define the material, which will be water for all the domains. This time, we choose incompressible to keep it simple, but Fidelity also features water defined by tables, which allows to model cavitation. Now we set the rotation speed, which will be taken by default by any wall patch pertaining to a rotating domain. And then we can move on to define the rest of the boundary conditions. For inlet, we're going to impose total quantities and velocity direction. Don't forget to set realistic K and epsilon values. You can find in Fidelity documentation some approaches that you can follow for this. Runner wall patches are rotating as we defined in geometry context. By default, force and torque will be computed. However, neither hub and shroud patches rotate as a whole, so we need to change them to area-defined rotation speed and define the limits of the rotating region in R and C coordinates. Outlet is set by default to static pressure imposed at atmospheric pressure. Finally, hub tip needs to rotate at the same speed as the runner. We have now finished defining the boundary conditions. Thanks to the coupled pressure-based solver fast convergence, we can significantly reduce the number of iterations. Before we start the simulation, we will move to result analysis context for defining some probes that will be used either for monitoring or co-processing. We will create a cutting plane at x equals 0 and add a color contour for velocity magnitude. We will also create another cutting plane, changing the type to blade at 50% of the span. And we'll add relative velocity vectors to check the incidence of the flow. To make sure that the field has been added, we click on this cutting plane, select Probe tab, and check that there is one probe of type vector field. Next thing that we will compute is the average of static pressure at the rotor stator on both sides, runner and draft tube. We can check the formula that will be used by clicking on the Info button. We will also set a 3D probe at the cone. We do it interactively by selecting the draft tube wall and then move it to the center by setting X, Y coordinates to 0. In Fidelity, 3D probes are shown as small spheres. If we click on Result Analysis View, we can see in one glimpse all the different probes that we created. We will create a new variable to compute the pressure coefficient at the blade. There are predefined formulas, but we can copy and modify them as we wish, and add or remove constants. Alright, now we can go back to simulation context and launch the simulation with 12 cores. After running for a few iterations, we will open the window collapsed on the left to see the residuals. We can go onto Result Analysis and do some co-processing. Let's show the cutting plane. We change to stripes mode, which is better to see the gradients, and we can change the number of ticks. We also see the 3D probe value. We check the incidence by way of the blade-to-blade cut at 50%. It's possible to easily reduce the vector size by modifying this parameter or simply moving the bar below it. Now we can create 1D plots. For that, we expand the window on the left. By default, we see the residuals, but we can split the window and add a new widget of type 1D plot. Rename as you wish. After that, it's time to select the support of the probe, which will be the intersection of the runner blade with the blade-to-blade plane. Click on Add Curve from Cutting Plane Intersection button and assign X and Y values. In this case, we select non-dimensional chord length and the blade pressure coefficient that we created earlier. Now we can see two curves representing the pressure and suction sides of the blade. We go back to simulation and change the residuals with inlet and outlet mass flow. We can modify the scale to see it more clearly. And rename the plot. We split the window and create a new monitor with the static pressure at the rotor-stator interface. And the 3D pressure probe. We rescale again and rename the series. Finally, we add a new window with the continuity residuals and rearrange the windows as we wish. The table below allows us to monitor a handful of quantities that are computed by default in Fidelity, including axial thrust, torque, efficiency, and power. The only thing left to do is wait for the simulation to converge. That's all. I hope that you enjoyed this series very much and look forward to help you achieve your goals in hydraulic engineering with Fidelity. Thank you for watching.